locally as well as on Blackboard. The recording from last lecture, the local recording I had was actually worse than the one on Blackboard. And again, I think it was because just having streamed on this surface for close to 3 hours, I think it was just really getting hot, and it wasn't liking me very much. But because we didn't meet in Capstone this morning, where I'm meeting with my teams one-on-one, so this is my first time using this today, so I'm hoping that this really sort of calms down some of the lag issues that we had, and there's kind of a pun in there because of our topic for today. But let's go ahead and get started. So the homework solution for 2.1 is posted, and that's been graded. You all turned in 2.2 today, and we had 2 assignments on gross and net area. This assignment and what we're talking about today sort of closes the loop on all of the dangling topics related to tension members before we can just get right into it. Because what you're going to see on Wednesday when we come back is we're just going to sort of get right into it. And the problems that would have taken, a couple of class periods, we'll be able to do in half an hour or so because we took time and handled all these tangential topics. In fact, I kind of want to, that's sort of where I want to start to sort of set the stage. So let me go back to, one of our first lectures and really sort of lay out the basis for what we're doing as structural engineers and what we're doing as designers. So if we go back to the base expression of LRFD, our fundamental goal that we're trying to achieve is that the resistance is greater than or equal to the loads. And that's just a really fancy way of saying, okay, I've got a tension member, and we're talking about tension members now, but what I'm saying here could apply to anything. It could be beams, columns, connections, it doesn't really matter. But the idea is I've got this element, we'll say it's a tension member for the purposes of our discussion. My camera doesn't really like the focus right now. This camera is not the greatest. I might need to consider getting another one. But anyway, so we have resistance greater than or equal to loads. The idea is that we look at the problem from 2 sides of the equation. On one side of the equation, we look at the loads. And so let's kind of look at the loads, and let's just sort of make sure we understand what we're doing with the loads. So, the first thing that we do is, we might have some load estimation. We might have some structural analysis. If we're looking at a particular member, and ultimately what we end up generating is a dead load on that member, maybe a live load on that member, maybe a snow load, so on and so forth. And then what we do is we take those and we put them through a series of load combinations, right? And so we had a homework assignment on those load combinations, like 1.4 times the dead, or 1.2 dead plus 1.6 live, and so on and so forth. And so ultimately what we're trying to generate is some factored load. So if we're in tension member land, we're trying to generate a PU, a factored axial load. So it would be MU if we were looking at beams, a factored moment, or VU might be a factored shear, or whatever. But the idea is to take these loads and factor them in order to attain a factored load. And then similarly on the resistance side, we're doing something very similar. So what we do is we identify a series of limit states. So we, for tension members, we might have yielding, fracture, buckling, whatever. And then what we're ultimately going to try and generate are a series of what are called nominal resistances. So maybe nominal resistance, and maybe I'll call that PN. Okay, so a nominal resistance is based off of mechanics and the specifications. So using some basic physics and some basic understanding of how structures behave, combined with specifications and insight into the specifics of steel, and we generate a nominal resistance. But this nominal resistance doesn't contain any type of safety factor, if you will. So the load combinations, they do, right? Because the load combinations, we're saying 1.4 times the dead, or 1.2 dead plus 1.6 live. So we're applying those load factors. We need to apply a resistance factor to this as well. So ultimately what we'll try and generate is a factored resistance. And so we multiply our nominal resistance by some safety factor, or we tend to call that a resistance factor. So we have a factored resistance and a factored load, and as long as the factored resistance is greater than or equal to the factored load, then we're good. And that's the basis, if you will, of structural design. We've sort of been dancing around that, and so I kind of want to get back into that and talk about that today. So again, recall this concept of LRFD. We're dealing in factored loads and factored resistance. So on the resistance side, we compute a nominal resistance based on mechanics, the specifications, and then we adjust it by an appropriate resistance factor. And so we end up with a factored resistance, and the same thing with loads. And as long as the factored resistances are bigger than the factored loads, we're good. Now, probably one of the best questions last week about everything that we had been doing was from Mr. Smirczynski, because he had asked, well, wait, if we were yanking on a tension member, and I kept talking about the piece of paper tearing right at my thumbs, and he asked, well, can it tear in the middle? And that actually was probably one of the best conceptual questions that entire week, because the answer to that, if we're talking about the piece of paper, is yes. And the same thing is true of the tension member. Let's go back to this concept of the gross section versus the net section. So in a tension member, not only are we looking at the net section, the cross section through that edge segment of bolts, but we also want to pay attention to the main body of the member as well, the gross section. Okay, so we have two different sections that we look at, and for each of those sections, we know that we can compute an associated section property. And what do I mean by section property? Well, for the gross section, the associated section property is the gross area, and for the net section, it's the net area. And I would hope by now that we're good on computing gross and net area, because we spent 2 days and have had 2 homework assignments just devoted to that, just devoted to the areas. But I want to sort of make sure that we understand the big picture. Now, let's go, what I think everybody ought to do is open up the manual again, and I want to go to Chapter D. I want to go to 16.1-28. Okay, so I'll do it with you. Go back to the specifications. Remember, the specifications have the letter chapters, and we're going to go to Chapter D. Let's see. So 16.1-28, and I'm looking at this section of the spec, and now I'm actually going to pay attention to it in a little bit more detail. I know we've kind of talked about it a little bit in passing, but today I really want to dig into it. And specifically, today we're going to focus on D1, D2, and D3. I'm going to talk about D1 later, but D2 and D3 is really what I want to focus on. What I want to focus on today. So let's start off with D2. Okay, so D2 states the design tensile strength, VPN, and the allowable tensile strength. So first off, anytime that you see allowable strength, that refers to ASD, and anytime you see the Greek letter omega, that's allowable stress design. And so in this class, we're just going to kind of ignore that because we're just using LRFD in here. So if you ever hear me read over that, it's because for our purposes, it doesn't matter. So the design tensile strength of tension members shall be the lower value obtained according to the limit states of tensile yielding in the gross section and tensile rupture or fracture in the net section. And so what we're saying here, if we go back to this, Mr. Smirczynski asked, well, can it fail in the middle? Well, yeah, it just depends on what you define as failure. So according to the spec, we limit the gross section to the yield stress, and we limit the net section to the ultimate tensile stress. So the limiting stress in the main body of the member is Fy. So that nominal capacity in the main body of the member would be Fy times the gross area, FyAg. Hence that first equation on D2-1, that's where that's coming from. And there's an associated resistance factor associated with gross section yielding, and that's a phi value of 0.9. Now, when we look at the net section, we limit the net section to Fu, to the ultimate tensile stress, and its associated resistance factor is 0.75. But let's pay attention to the spec here a little bit, because the yield for the gross section, look at the areas. The area is Ag, but what about the net section? The area is not An, it's this term Ae. What the heck's going on with Ae? Well, look at section D.3. Ae is the effective net area, and if you read the spec, it's the net area times this term U, a shear lag factor. And that's sort of the big topic of today is shear lag and slenderness, because I want to talk about D1 as well. So if we summarize our expressions for phi-PN, right now we have two limit states to assess. We have a phi-PN for gross section yielding and a phi-PN for net section fracture. So for gross section yielding, if we want to compute phi-PN, we take 0.9 times Fy times Ag, and for net section fracture, 0.75 times Fu times An times U. So I know there's a lot of terms and a lot of values. We're actually going to use a lot of this stuff on Wednesday, but I just want to introduce the big picture ideas today. So let's digest this a little bit. First off, let's talk about the safety factors or the resistance factors. So the resistance factor for yielding is 0.9 and the resistance factor for fracture is 0.75. So why is the resistance factor smaller for net section fracture than it is for gross section yielding? Well, it all has to do with uniform levels of safety, and it has to do with the expected outcome. So if you have a member and you take that member and you yank on it, and the main body of the member reaches Fy, what happens? What actually physically happens? Well, if the main body of the member reaches Fy, it begins to yield and it begins to permanently elongate. That's what happens if we violate the gross section yielding limit state, is that the member permanently gets longer. But for net section fracture, what happens there? Well, if we exceed that limit with net section fracture, we're not talking about permanent elongation of the member. We're actually talking about fracturing the member in half. That's not a good day. So it would make sense from that perspective that the usable strength should be lower, right? I mean, again, if a member experiences permanent deformations, that sucks, but all that's really happening is it's just getting permanently longer. But if you exceed net section fracture, you're snapping that thing in half. So that's not a good day. Hence why the usable strength is lower. We have a 0.75 as opposed to a 0.9. All right, so that's sort of my first point I wanted to make. Second point I wanted to make is let's look at these terms in these equations. Okay, we got 0.9 and 0.75. Those are just numbers. Ag and An, hopefully we beat those into the ground. Fy and Fu, we had an assignment devoted specifically to that. Just what is Fy and what is Fu for various grades of steel. If you have a W section and that W section is made out of A992 steel, A992 grade steel, you can look up the properties for A992 steel and you know that Fy is 50 KSI and Fu is 65 KSI. They're just lookups. So the one thing that's sort of sticking out is this term U. Okay, so when we come back Wednesday, we're really going to just build this out and do a full-blown tension member analysis start to finish. And once we know how to analyze a tension member, I think you'll sort of get an idea as to how to design one, because this is steel design. That's sort of the point. All right, any questions before I dig into shear lag factors and what they are and why they even exist? Man, I'm getting off easy. Okay. So let's talk about shear lag factors. So if you notice, if you go back to the expressions here, those two expressions are largely identical. There's a safety factor, there's a limiting stress of a material times an area. But there's something different on the net section fracture expression. So for yielding, it's resistance factor times limiting stress times area. For the net section fracture, resistance factor times limiting stress times area times U. What is different about the net section that we don't need to account for in the gross section? The difference is this, okay? So all too often, or very often, when we actually construct a tension member, we don't connect all of the cross-section components, okay? What I mean by that is, let's take a look at this I-beam, or this W section over here on the bottom. So if you look here, you can see, let me use a bright color here. So you can see we've connected the flanges. But notice how we have not connected the web, okay? So not all of the cross-section components are connected, only some of them, okay? And it's not only just that, just the physics and the mechanics of connections in general tend to create non-uniform stresses around the connection. When you break out a full-blown like abacus 3-dimensional finite element analysis and you do the nonlinear analysis of a tension member subjected to the types of loads that you see in structural systems, what happens is this: when you look at the main body of the member, like down here or down here, this is the gross section. Okay, that's the gross section. And what you're seeing over here on the right is what's called a stress contour. This is what finite element packages like Abacus or ANSYS or what have you. This is really powerful software that's used in research and really complex engineering. But when you look at the main body of the member, you see that the stresses are fairly uniform. If you look at the bottom of those images, they're yellow, which is basically saying there's no change in stress, that they're all the same. But if you look like right here, at the net section, or right here where the net sections are, the stresses are weird. They're not simple. They're funky. They're all over the place. It takes time for those stresses to propagate and distribute throughout the tension member. See, out in the gross section, the stresses are pretty uniform, but right there at the connection, they're weird. They're just they're difficult to handle. What ends up happening is, the reason why the phenomenon is named the way it is so let's say you have an angle. Okay, here I'll turn my camera off so you can kind of see this. So let's say you have an angle, right? So there's a sort of a plate and a plate like this. Okay, and let's say that this hand right here is bolted to a given element, but this one is not. Okay, and so when I yank on that member, I'm not yanking on the entire angle, I'm only yanking on part of it. So the other part of it is kind of lagging behind. It's as I yank on it, my left hand here is wanting to receive the load, but the right hand is sort of lagging behind. It takes a little while for those stresses to propagate throughout the section. And because my hands are sort of doing like this, it's kind of like an internal shear going on in the sections. That's why we call the phenomenon shear lag. Now, here's the thing. Shear lag is a complicated topic. It's not easy to deal with from a research side of things. You have to do some really complex modeling. If you really wanted to capture it, you could go down to the lab and break a bunch of tension members and whatnot, which is fun. I mean, any day with controlled demolition is a good day. But that doesn't really address your problem as the designer. I get that it's complicated. I get that it's a challenging problem, but you still need to deal with it. You still need to be able to accommodate this in your design, but you need to be able to do it easily. You don't want to have to do a complex, full-blown finite element analysis for every tension member that's in the roof system of every gymnasium that you design. You need a simple, practical formula that you can use to deal with this. So that's where empirical expressions come into play, and that's where the value of researchers like myself come into play. I mean, that's sort of what we do, is we do all of these, run all these models and do all this testing so that we can come up with simple, practical expressions that folks like you can utilize. I want everybody to turn to 16.1-30 in your manual, okay? So this is, if you were with me on Chapter D, it's the next page, okay? And it should look like this. Table D 3.1, shear lag factors for connections to tension members. This is a table that's worth tabbing or putting a bookmark or a sticky note or something. Like on mine, it's tabbed, I just put U on the tab, the letter U. But this is a very valuable place to have bookmarked. This lists the shear lag factors for just about every connection scenario that you would need, and not just every connection, or not just about, it actually really is every, because of the way that case 1 and case 2 are written. There's a couple things I want to get across. Okay, the way that these things are derived is just like I said. They go down to the lab and they break apart 100, 200 different tension members, and they record the data, and they try and fit an expression that matches the data as closely as possible, but without making the expression too complicated, right? So there's a little bit of a trade-off, and what I would say is I think that the resulting terms are pretty simple to use and also pretty effective. Now, keep in mind also, and this is another point to make, multiple cases could apply to a given connection. So we'll find instances where we'll use case 2 and case 7, or case 2 and case 8, or whatnot. That's very common. Keep in mind these are empirical, so these are, again, the best fit to the data, and they do have some behavioral backing behind the way the equations are constructed. But again, the idea is to try and keep it simple. Okay, and I think you'll find this is a pretty simple concept. First thing I want to do is I want to go into this table, and I want to focus first off on case 1 and case 2. Okay, and so let's read these together, and I'm going to go through what's in the manual, and what you see here on the slide is pretty similar. But case 1 and case 2 really set the stage for the entire situation we're dealing with. So case 1, all tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds, with some exceptions, we take the shear lag factor to be 1. And so what that means is if you have a cross-section, like the situation I was looking at before with the wide flange here, what if it's the flanges and the web? What if they're all connected? If all of those components are connected, for simplicity, we take U to be 1. Okay, so if all the cross-sectional components are connected, we really don't need to consider that stress discontinuity too much. However, again, what's very often is that the load is transmitted to some of the cross-sectional elements by fastener welds. Not all of them, but some of them. So, an angle that's only connected with one leg, or a channel that's connected by the web, but the flanges are left unconnected, what have you. That would be a case 2. And case 2 is probably the most fundamental one that you need to understand. And the formula for case 2, if you read the manual, is 1 minus X bar over L. And admittedly, the L is kind of tough to read because it's this little tiny squiggly thing. But what I've done here in the slides is I've defined that with a little bit of a different symbol that I think explains what's going on a little bit better. So U sub 2, which is sort of the mainstay formula, is 1 minus X bar over L, but it's specifically X bar for the connection and the length of the connection. And I'm going to define what each of those mean here in a second. I saw a hand raise. Who was that? It's not popping up here. Mr. Enod, I think that was. Oh, don't worry. I'm going to define. I've got like 3 or 4 slides just devoted to that. Don't worry. Any other questions? This is good stuff. Okay. Now, a couple things to keep in mind. Like if you look at some other cases, like case 4 or even case 6, you'll even see 1 minus X bar over L in those expressions. Now, some of those are hyper-specific cases, like if you have a tension member that's a round tube and you have a knife plate connection through it, then you're using 1 minus X bar over L, and it's just telling you what the X bar terms are and what have you. But in most instances, you're going to have to sort of figure out what X bar and L are, and that's sort of what I want to try and define. So X bar, I call it X bar CON, sub CON, because it relates to the connection. And really X bar is what's called the connection eccentricity. And so the best way to define that would be the distance from the connected face to the centroid. Okay, so let me give you an example. And I'm going to turn my camera on here so that you can kind of see what I'm talking about here. So, all right, so let's say for the sake of discussion that you have a channel. Let's say you have a channel. So here's the channel. Okay, so here's the channel. Now the centroid of a channel can sometimes not be on the channel. Usually it's sort of like right there. So it's, halfway, top to bottom, and it's a little bit further out. Okay? And let's say that this channel is connected via the web. Okay? So let's just say here's the bolts going through the web. Okay? Now think a little bit further ahead. what is this thing going to be connected to? Well, I mean, there's probably going to be some plate or something out here that it's connected to, and those bolts are going to be going through the channel, right? I mean, it's got to be connected to something, right? So what I would suggest is this back of the channel, that this face right here, this is the connected face. Like the back of the channel, because that's what's going to be butting up with whatever it's connected to, right? So this is the connected face. That's the centroid. This dimension is X bar. That's your X bar. Okay? So what it requires really two skills. One, you have to be able to, look at the member and look at the situation and identify the connected face and identify the centroid so that you can identify, okay, that's the dimension I need. I need that dimension. So that's the first thing that you need. The second thing that you need is you need to be able to open the manual and pull that dimension out of the specs. That's where those schematics come into play. If you remember, I had mentioned, make sure that you're following those schematics on the top left so that you can, look at the shape and go, okay, that's the dimension I want. Now, a couple of things. So you can look right here in the slide. This is this image on the bottom. That's kind of what I was showing. That if you had a channel with the bolts going through the web, then the connected face would be the back of the channel. The centroid would be there. So that's the X bar. Now, if you open up channels, just to use channels as an example, well, the X bar connection value that you need is actually just X bar for the channel. So you can just look up X bar and use that value. But that isn't always the case. You just have to make sure that you're identifying the dimensions appropriately. And don't worry, we're going to have some examples looking at this. Now, this yellow box is kind of important, and I want to make sure everybody's paying attention to this. So I want everybody to turn to page 1-38 so that we're all looking at the channels. So I want to make sure that we're clear on this. And you could look at the channels or the angles, but just to make sure that we're on the same page. Actually. So 1-38, I'll give you a sec on that. And go ahead and leave it on 1-38 because we're going to use that page for an example that we're going to do here in a second. I'll give everybody a sec to turn to that. Sorry. All right. I'm going to assume everybody found it. If you didn't find it, let me know. But if you look at the C shapes, so on the left page are all the dimensions, the right page are all the properties. And I want to look at axis YY on the page on the right. And so so you should see 6 values, 6 properties listed. So there's an I, that's the moment of inertia. S is the section modulus. R is the radius of gyration. We'll talk about the radius of gyration actually here in a bit. And then there's X bar, and then there's X sub P. Don't use the X sub P values. Don't use the Y sub P values. If you ever see those, don't use those for now, okay? Without getting too far down the rabbit hole as to what those are, I'll say 2 things. One, we will define what those are later. Don't worry. We kind of have to define what those are in order to handle beams. So we will define them. But to satisfy some curiosity that I'm sure some of you have, the X sub P values and the Y sub P values refer to what I'll call a different centroid that is specifically related to bending. And we're not going to use that now because what we need is the location of the neutral axis, the geometric centroid of area, and that's the X bar or the Y bar. So just don't use the XP or the YP values for now. We will discuss them later. All right. Now, another thing I do want to mention, and we're not going to employ this today, but we will employ this Wednesday, is there is a special case for the X bar connection, and that's W sections that are connected via the flanges. And what we do with a W section that's connected via the flanges is, in order to determine that X bar value, what we do is we sort of conceptually split the section in half, and we look at an equivalent WT section and look up that centroid, which ends up being the Y bar value for that equivalent WT. And so if I had like a W12 by 30, if I cut that in half, well, it's half as deep, so it's a WT6, and it's half as heavy, so it's a WT6 by 15. And so I look up the centroid for a WT, an equivalent WT, which would be a WT6 by 15, and I use that centroidal distance as the X bar for the W section. Again, as I mentioned earlier, these are empirical expressions, so this fits the test data pretty well. The idea is that if you load the section, the idea is that if I'm looking at this I-beam, like half of the load goes to the top portion, half of the load goes down, hence why you use the WT. Does the orientation of the beam affect the X bar? It can. It can affect what value you look up, absolutely. And so that's where the schematics and your understanding of how the member is proportion do matter. So, but don't worry, we're going to get to some examples on that. I'm not going to leave you hanging. The connection length is actually pretty easy. It's just the out-to-out distance between the centers of the bolt holes. So if you have a grid-like pattern, just however far your out-to-out bolts are, if your connection is staggered, like you have here, just the out-to-out distance. Now, probably the most common mistake is sometimes students will include that distance. You do not include that distance. You only include the out-to-out center-to-center distance between the bolts. So yeah. For welded connections, and again, we'll talk about welded connections probably a little bit more in depth later, but for welded connections, we just take the average length of the fillet welds that connect the section. We aren't going to really need to worry about that today, but you have that just for your reference. Now, before we get into an example, and I'm going to hold off on questions because I think that some of your questions will probably be allayed, and you'll have a bit more context when we start doing a problem. And I've got two problems here in a bit, and I think you'll find this is pretty simple. But I do want to talk about slenderness limits because it is another check that is kind of important. But I say slenderness limitations or lack thereof because if you open the spec, so if we go back to Chapter D, and you don't need to turn to that in your manual, but if you want, you can. But if you go to Chapter D and go to Section D.1, this is what it states. There's Section D.1, slenderness limitations, and it sort of only has one sentence. There is no maximum slenderness limit for members in tension. And so some of you are probably thinking, well, if there's no slenderness limit, why the heck are we talking about this, Dr. Mike? Well, read the user's note below that, and the user's note says, for members designed on the basis of tension, the slenderness ratio, L over R, which L over R is our definition for slenderness, preferably should not exceed 300. Now, slenderness limits, first off, what is the deal with the slenderness limit? Why would we employ that? Steel in its, intact, erect, structured, system state can be a pretty stiff system, but as you're putting it together, sometimes steel can be a little tough to handle if it's really slender. The members can have a lot of seg. They can have damage during shipping, damage during erection. If you've ever been in a fabrication shop and you see them fabricating like a plate girder, when they're manipulating the plate, that plate picked up the wrong way can have about as much stiffness as a piece of wet spaghetti. So it's kind of strange. I remember being at a fabrication shop and there were some I-beams, sit down, and these I-beams were 100 feet long and they were yay deep. And because I was bending about the weak axis, I was able to just do that and bend it with my hand. Not because I'm some Kryptonian Superman or something, but because just in that direction they were pretty weak. And that's not how they were intended to be in their final state, but that's kind of the point I'm making. Slenderness limits are really kind of important, and this term L over R, which is our definition of slenderness, is going to be really important later. L over R is a great mathematical definition of slenderness. So first off, L is the member length and R is the radius of gyration. And how do you compute the radius of gyration? You just take the square root of I over A. I being the moment of inertia and A being the cross-sectional area. So you could think of R as like sort of a normalized expression of the moment of inertia. But when you take L over R and you divide them, it's unitless. So slenderness, one of the beauties of that definition is that there are no units associated with it. And to give you some context, if you compute the slenderness of a soup can, you're probably going to get an L over R value of around like 6. And then take that all the way to like a dry spaghetti noodle. The L over R for that would be like 500. Slenderness also is very, it scales well. So if I had a piece of spaghetti in my hand and then Ant-Man decided to make me, shrink me to, that tall, and I computed the L over R of this, of the spaghetti when after the Ant-Man transformation, it would still be the same slenderness value. So L over R handles the scale quite well. And then Slender Man, who knows what the slenderness value is there. That was just my poor attempt at a joke. So when we compute slenderness, we take basically the limit we're going to utilize is L over R has to be less than or equal to 300. The thing to keep in mind is if you pull the R values from the manual, radii of gyration are listed in inches, but when we're talking about the length of a member, we tend to express the length of a member in feet. So we need to convert the member length to inches so that the L over R term is unitless. Okay, so that's an easy thing to mess up. For the radius of gyration, what we care about is, this is from a handling perspective. So we just want to use the minimum radius of gyration that's available for the shape, because that'll yield the maximum slenderness. And really what we're trying to do is just ensure that the shape isn't too slender. So we want the worst case scenario. So for symmetric shapes like W shapes, like WTs, like channels, just use the minimum of whatever RX and RY are. But for angles, you're going to use the minimum R overall. And for angles, you'll see that there's an RX and RY, but there is also an RZ. And that's because angles aren't symmetric with respect to the X and Y axis. So there's a principal axis that you'll want to use for angles. Okay. Let me introduce our examples, and then we'll start digging into these. So I've got two different shapes. We've got a channel and an angle, and I want to determine the U value for each of these, and I want to see also, just off to the side, does the channel meet the 300 L over R limit if the channel has a total length of 15 feet. So if that channel is 15 foot long, does it meet L over R limitations? Okay. Any questions as I pull up the notebook? Everybody good? Okay. All right. So, yeah, my surface is already getting a little warm, but hopefully it holds up all right. Okay. So let's take a look at this this shape here. So let's look at the channel. Okay. So the first thing I want to determine is, if we're trying to determine the shear lag factor, first off, let's see if we can determine, I don't know, the length of the connection. Somebody in chat tell me, what is the length of the connection for this channel? 9, okay? It is 9 inches. The point I want to make is that it is not 11 inches. It's very tempting to include that 2 inches, okay? But the connection length is just out to out from exterior center lines of bolts. So we're using the length of the connection as 9 inches, okay? Now, what about the X bar, okay? Well, let's go here. So, I'm looking at this shape, or this diagram right here. So the centroid is probably going to be somewhere about like that, and the connected face is going to be, like this face right here. So ultimately what I want this dimension. That's X bar. Now, hopefully you all have your manuals open. So X bar now we have a C10 by 30, okay? So this is the shape that we're dealing with. So for a C10 by 30, and I've already got a lot of people in the chat responding, and I love it. So X bar for a C10 by 30 is going to be 0.649 inches. Now, and that is correct, okay? Now, 0.649 inches, that is correct. Now, what I want to be clear on is that, you know, we're calling it X bar here, and the reason that you pick that is X bar for a C10 by 30, but sometimes it could be Y bar, you know. I just want to make sure that you recognize that this is the dimension that we're after. We're after that X bar connection, and that just happens to also be named X bar for this section. Doesn't always have to be the case, just something to keep in mind. Somebody raised their hand. Who was that? Just Mr. Adkins. Sorry about that. Let me see. It's not quite too. My surface isn't totally hot, but it definitely is a little warm. I just don't think it was designed to do all this streaming that we're doing these days. Okay, so if we have our X bar and our L, we can compute U2, which is 1 minus X bar over L, which is 1 minus 0.649 inches over 9 inches. And what is U2? $0.928. Do I have a second on that? Good deal. All right. Now, just so we're on the same page, I'm going to turn to the shear lag table. So this is the U value for case 2. All right. I just want to make sure that we're clear on something. Do any other cases apply? Mr. Enoch. Oh, it doesn't. It doesn't. That was a mistake. I was just getting ready to point out that it's also unitless, and I wrote the inches, Mark. You are correct. Whoops. You're absolutely correct. Okay, going back to table D3.1, are there any other cases that would apply? Now, a quick review is going to find that no, there aren't, because case 3 is about welds. We don't have any welds. Let's see. Case 4 is about welds. Case 5 and 6 are about HSS. Case 7 is about W shapes. Case 8 is about angles. So nothing else applies. So the only case that applies is U2, and U1 doesn't apply because the flanges aren't connected. So therefore, U equals U2 equals 0.928. Okay, so that's the answer. And since I've already got the image pulled up, I'm going to go ahead and ask this question. Let's talk about the slenderness. Now, let's go back to the channels section, and I want somebody to tell me what is the smallest R value. Is it Rx or is it Ry? And what is that for this channel? So we're looking up a C10 by 30. What is the minimum R value? And this is symmetric, so you aren't going to find like an RZ. It's either going to be Rx or Ry. Ry. And it's 0.668 inches. Okay. Now, in the problem description, this member is 15 feet long. Now, if I take L over R and I take 15 and divide it by this, that's not going to work because 15 is in feet, the R is in inches. So we're going to convert this to inches by multiplying by 12. And so what is L over R? You did. I think you might want to check the, there we go. So 269.5. So, no, you're fine. So does this meet our slenderness check? Yes, it does. And so in structural engineering land, and you'll see this a lot, I'll put like a therefore, and I'll put okay. Sometimes you'll either see okay or the letters NG for no good. And so OK means that it meets the slenderness check or whatever check that we're talking about. NG means it's no good. Okay, so that meets the check. So on your homework, you have a problem where you just have to do something very similar. Okay, I want to see if we can knock out this one real quick. This is an L 8 by 8 by 5/8. Real quick, can somebody tell me what is the length of the connection? Let's see if anybody can eyeball that. And remember, the definition is we go from out to out. That is LCON. And so I've got 10 inches. That is correct. Now, how about the X bar? Now, here's a little trick. Which value do we use? X bar or Y bar? Actually, a better answer is, well, here, how about this? A better answer is, does it really matter? It's an L 8 by 8. X bar and Y bar are the same. Now, X bar is specifically the centroid from the long leg, and Y bar is the centroid from the short leg. But in this particular instance, it doesn't really matter. Does anybody have X bar for the L 8 by 8? By 5/8, 2.21 inches. So therefore, U2 is 1 minus X bar over L, which is 1 minus 2.21 over 10. And so what is that? I think, anybody have an answer for that? I know we're running short on time, so I might put a rush on this one, but 0.779. Okay. I want to show you something real quick before we call it. If you open up the manual and you go to D3.1, let me see if I can pull that up super quick. All right, so I think my camera's not liking me very much, but oh well. Let's follow with me along in the it's on 16.1-30. Now, if you go to table D3.1 and you specifically go to Case 8, okay? Case 8 states that for single and double angles, we also have another case. But if you read this carefully, it says if U is calculated per case 2, the larger value is permitted to be used. So in this instance, we actually have two different shear lag factors, not only U2, but U8. Now, if we look at case 8, case says, okay, we have a single angle. We have either 4 or more fasteners per line in the direction of loading or 3 fasteners per line in the direction of loading. And for our angle in question, we have 3 fasteners per line in the direction of direction of loading. So we're going to be using a U value according to case 8 of 0.6 because we have 3 fasteners per line. So this is going to be, U8 is 0.6. And I'll put, 3 fasteners per line. But the spec says that of these 2, we take the maximum. And again, that just fits the behavior the best. That's sort of think of the U8 as sort of a lower bound. So therefore, U is U2, which is 0.779. But it very well could have not been U2. It could have been U8, depending upon the way our connection is arranged. So in those instances, we need to evaluate both and then take the one that controls. Okay? And so the U section is on 16.1-30 to answer Mr. Smirchinsky's questions. I know you all have class coming up, and I know I ran over a bit. Any quick questions before I call it? All right, well, I'm going to go ahead and stop the recording. It's a very short homework assignment related to this, and then on Wednesday, we start doing this for real, start to finish tensor member analysis. I think you'll like it. Okay, that's all I have, everybody. I will see you all on Wednesday.